Hi, my name is Jerry Nelville, and today I will be explaining the problem that's number 2 on our second midterm, which is also a homework problem on relativistic collisions. Now, the problem talks about photons and mass particles. The initial thing is that a photon approaches a particle at rest with mass m, and then it deflects off perpendicularly with a new energy, and that's what we're trying to find. And the mass comes off with velocity v at angle theta, and it still remains at the same mass. Now, the thing about relativistic collisions is that you're always going to want to do conservation. You want to do conservation of energy, conservation of momentum in the x direction, and conservation of momentum in the y direction. In relativistic collisions, everything remains there. In normal collision, you might not always be able to have conservation of energy because you'll have inelastic collisions, but in this case, everything stays in there. So let's start writing out the 3 equations for those things. Now the first one is conservation of energy. Conservation of E. So if you look at the system at the beginning, there is the energy from the photon, which is E, and then you have the energy from this particle at rest. Normally, in normal collisions, we'd say that it has no energy, but in relativistic collisions, we say it has a resting energy of mc squared. So you're going to have E plus mc squared as your initial. Now, if you look at the system at the end, you're going to have this new energy, E prime, and then you're going to have the new energy caused by this. Now, the way you find that is by using gamma. So you're going to have, and the gamma factor, so in this case, rest energy is mc squared. The energy in movement is gamma mc squared. So you're going to have E prime plus gamma mc squared is equal to your final energy. So now that we have conservation of initial and final energies, we'll do conservation of the other things. The next step is conservation of momentum in the x direction. You can either do x direction or y direction first, it really doesn't matter. I just like to go with x. Conservation of momentum in the x direction. Now, initially you have a particle at rest and you have a particle that is moving, and that in this case is the photon. However, you might think, well, it has no momentum because it's massless. For our cases, and something that we have found in the notes and in lecture, a photon has the momentum of E over c. And then you can see this particle is at rest, so it has no momentum, and it is a particle with mass, so no momentum. That means our initial is E over c plus 0. I'm putting the plus 0 there so we can keep track of where we got everything from. The final, however, you're going to see that this particle is moving vertically, and it no longer has any movement in the x direction, so that means it has no momentum in the x direction. However, this particle down here will have movement in the x direction as it is deflected off by angle theta, so that means mv cosine theta is going to be that value. So you'll have 0 plus mv cosine theta as your final. Now, since we just did conservation of momentum in the x direction, we'll do conservation of momentum in the y direction. Cons of py. Now, similarly, as you can see, there's no movement here in the y direction, so that means there's no initial momentum in the y direction. So 0 is equal to initial. Now the next step is going to be finding it for the final. You're going to have this, which is just going to be E prime over c, using the momentum that we found earlier for photons. Again, energy over c, the energy of this is E prime. Now the next one is mv sine theta. However, this one's negative. Since this one's going down, we're going to subtract it from whatever the momentum is here, and then we're going to end up with our final momentum, which will end up being 0 since it's being conserved. So E prime over c minus mv sine theta equals final. Now, some things that we can deduce are by looking at here, we see these are the 4 energies for the 4 different particles. Let's work with the very important relation, which is something that we have to use over and over again in relativity, which I've written right up here. E squared equals p squared c squared plus m squared c to the 4th. Let's rearrange this to put it into isolate something that we know everything about, and you'll see why we do that later. Conservation of energy requires us to make things equal. So E plus mc squared equals E prime plus gamma mc squared. We'll isolate this, so we have E plus mc squared minus E prime is equal to gamma mc squared. This component is the energy of the particle over here, and this is equivalent to that energy. Now, the next thing that we're going to want to do is finding the momentum. So we can plug it into the formula over here. Now, that momentum can be found by dropping the c's and by summing them together. The initial momentum and the final momentum, you can see as E over C is equal to mv cosine theta. And over here, E prime over C is equal to mv sine theta. Now, using these three, we can use the very important relation. Again, one strategy that we use is we drop the c's and then put them back in because they do make the calculations a little bit harder. So, using the very important relation, and we're using this in reference to m. As you can see, mv cosine theta is the momentum in the x direction of m, and then it's also equal to E over C. Mv sine theta is the momentum for m, and then it's also equal to E prime over C. The reason we do this is because we're trying to solve for E prime, and that way we can have everything in the equation. So let's plug it into our very important relation. E plus mc squared minus E prime squared is equal to, and remember we're dropping the c's, so I can get rid of that c right over there too. Sorry about that. Okay, is equal to the square root, and because I'm adding these together through vector addition to find the actual momentum, the square root of E squared plus E prime squared plus m squared. Now, the rest of this problem is really just a lot of calculation. So I will get started on that, and I'll do that right over here so we have a clean, nice space for it. I always like to break this apart into its components just because it makes it easier for me, but I'm going to skip the foiling because that'll just take a while. You have E squared plus EM minus E prime plus EM plus M squared minus E prime M minus E prime minus E prime M plus E prime squared. And this will be equal to E squared plus E prime squared plus M squared. I know this is a little sloppy, but just stick with it. That is a long foil. Then what we can do is cancel out terms that we see. We can cancel out E squared, M squared, and E prime squared because they are also on the right. Now we're going to end up with EM minus E prime plus EM minus E prime M minus E prime minus E prime M equals 0 because everything on the right side canceled. Now we're going to combine like terms. As you can see, there are many of them. You're going to have 2EM minus 2E prime minus 2E prime M equals 0. Then you can cancel the 2's. EM minus E prime minus E prime M equals 0. And then you can add both of these to one side because we're trying to isolate E prime because that's what the question is asking for. I'll just draw this over here. EM is equal to E prime plus E prime M. Take out E prime and divide. So you have EM is equal to E prime times E plus M. Therefore, E prime is equal to E M over E plus M. However, you may think that we're done, but we're actually not. The units really don't match up for this thing. The way that we can make the units match up in the end is by putting the c's back in. The best way to do it is find the mass and multiply that by c squared, wherever it's contained, because in the numerator we're going to have too much energy and the units on the bottom won't match up with it. So this is actually equal to E mc squared over E plus mc squared. Because this is going to double the energy units, but this is going to cancel them right back out, and you'll get the units for energy, which is what we needed. And that is relativistic collisions with photons.